Hello, it's 12 a.m. of morning. Today is 14th March 2025. And I was in my room. I was thinking to read Algebra by Israel Gelfand for some time. I was thinking of reading this book because I I wanted to read it basically. So this book is about algebra, right? This covers a lot of it covers a lot of topics. These are the topics which most of the people which are into STEM already know, but I wanted to refresh my knowledge about them. I wanted to have a good knowledge about them, so if someone pull out something related to these kind of things, I should be probably able to solve it. I should probably able to think about it. I should be able to speak on it, think about the mathematical algebraic way. Let's start from the basic. This book is about algebra. It's great. Very old and extensive process terms for videos. Nice. Uh, so it would be much better. Grab paper and pen. This is like the associative law. Okay, to exchange terms of multiplication. I was always seen multiplication as if 2 multiplied by 2, it is like adding 2 times into itself. Similarly, 3 multiplied by 4 will be like adding 3 4 times or adding 4 3 times. But I never really understood the way it is shown in this book. Multiplication has similar property. The property which they are talking about here, it is 3 plus 5 is equals to 8. Similarly, 5 plus 3 is equals to 8. Now we see that these two equations, they're pretty same. They're like a bunch of same pretty useless, boring equations. But still, if you think about this way, that if we add 5 apples into 3 apples, we get 8 apples. And if we add 3 apples into a group of 5 apples into a basket of 5 apples, we get 8 apples. Similarly, if we think about multiplication in such a way, it has a similar property. But let us first agree on notation. Usually in arithmetic, multiplication is denoted by, okay, in algebra, in arithmetic, we represent multiplication by this, but in algebra, sign is usually replaced by a dot. We follow this convention. Both are 15, but it's not so easy to explain why they are equal. Okay, so here comes the solution. One of the authors of this book asked a 7 years old girl, how much is 2 times 4? 8, she answered immediately. And 4 times 2? She started thinking, trying to add 2 plus 2 plus 2 plus 2. A year later, she would know very well that the product remains the same when we exchange factors, and she would forget that if it was not relevant before. The simplest way to explain why 5.3 is equal to 3.5 is to show a picture. So this is a very, very elegant demonstration of why both of them are equal, while this equation is true, why it holds true for every number. So if you try to think about in a perspective of area, geometrically, the area remains constant. For example, if you have a rectangular box, probably the phone screen on which you are watching this, the laptop screen on which you are watching this, even if you rotate your phone screen or laptop screen, the size of the screen, the area of the screen is going to be same. It's going to be same how it was before rotating. Because rotation, it's pretty evident that rotation is not going to change the area of the phone screen. Similarly, we are rotating the number of apples in rows and columns. We are basically taking the transpose of it, and this thing is not going to change the number of apples, basically the area of the rectangle, which is the number of apples. This makes it pretty evident why multiplying two numbers and rotating them and then again multiplying is going to be the same. This is the same thing which I explained earlier, like 7 apples and 9 apples near them, and then count all the apples together. 1, 2, 3, 4, 5, 16, 16. We get 7 plus 9 equals to 16. This method can be applied for any numbers. However, you need a lot of patience to write on, say, 137 and 268. So mathematicians invented other methods. One of them is the standard addition method used in positional number systems. So I actually also wanted to read this because it gives a really good insight into our decimal number system, right? We are so used to decimal number system. So, like when we think about addition, which is very basic, fundamental thing, which is taught in our school, which is taught like in which our methodology is taught in school, like you have to take the carry adds to the next number, and then if again carry comes, it goes to the next number. It will continue until the last number. We start from the right, but never really told why we start from the right. Why can't we start from the left? If asked, such if we try it on our own, we understand that how can we take the carry if we start from the left? That is actually right. That is really good, right? That's a valid point. But still, this kind of addition algorithm, this kind of addition method is only true if we use positional number system. It is written how one of them is the standard addition method, which is taught in our schools, in our junior classes, used in positional number system. Positional number system, what do they even mean by positional number system? Positional number system are the number systems like which we use regularly, like binary, like decimal, like hexadecimal, octal. All we don't use binary, octal, and hexadecimal as often as we use binary. Binary is the like core of mathematics, the core of mathematics that is taught in our school. Binary is pretty popular in computers. Computers can only understand ones and zeros. They rely on binary, and octal and hexadecimal are number systems which do exist, which are used less by computers, pretty less by computers. Core of computers run still on binary, and octals are also a kind of neglected number system. They are all positional number systems. The positions of the number define the variations of number, the value of number, the actual value of number, if you can understand what I want to say. There can be other types of number system where the position doesn't explain the number, the value of number, rather the frequency of the numbers explain. In such number systems, it becomes really important. It becomes pretty evident that why can't we use the standard addition method, standard addition approach to add to numbers? Because the number system on which you are working plays really evident role in the methods that you have to follow for addition, for subtraction, for multiplication, and for that, for thinking in that perspective, for doing work in that perspective, it is really important to understand the fundamentals, to understand the for understanding this kind of very fundamentally algebra, fundamentally numbers understanding, and to have a great understanding of mathematics. I was okay in maths, so I always wanted to rebuild my fundamentals from zero. It's a step towards that goal. Different countries at different times people use different notations for numbers. An entire book was written about them. We are so used to the familiar decimal number system, 0, 1, 2, 8, 9, that we don't realize how unbelievably convenient this convention has proved to be. Even the possibility of writing down very big numbers quickly was not self-evident for ancient people. A great mathematician of ancient Greece, Archimedes, even wrote a book called The Sand Reckoner. The main part of the book was to show that it is possible to write down the number that is greater than the number of sand particles filling the sphere whose radius is distance between Earth and the stars. Now, the decimal number system has no rivals except the binary number system, which is a pretty popular among computers, not people. This binary system has only two digits, 0 and 1. But numbers have more digits. The computer does not worry about the length of. But numbers have more digits. Okay. The computer does not worry about the length of numbers, but still wishes to keep rules of operation as simple as possible. That's true. We can, for example, we can write 2, 1. If you want to write 21 in decimal, it will be 2 and 1. But if you want to write 21 in binary, that is going to be 10101. So we got five numbers in binary, five digits in binary, where it can be only done with two digits in decimal. That's why you can understand why decimal is much preferred over binary. Actually, we could have used a number system where there would have been more numbers than 10. For example, 16, which is hexadecimal. But actually, we are so much convenient, we are so much used to decimal numbers that thinking in hexadecimal way becomes like not an intuitive way. It is not intuitive for us humans. Several 8 digits are written and some plus signs are inserted to get the sum thousand. Figure out how figure out how it is done. For example, if we try to 88 plus 88 plus 8 plus 8 plus 88, okay, thousand, we get the thousand. If we first try to do 8n is equals to 1000 and try to find the value of n, that is that will be probably, let me grab paper. 8n 1000, so n is going to be 500 by 4, 250 by 2, 125. Okay, so we can at least we need 10 8 to get 8 at last. Maybe 5 8. Huh. We need at least 5 8, because 5 multiplied by 8 is 40, so we need 5 8 here. We do not know how many rows and nor know how many digits are used in each number. Each number ends with 8 and the last digit of sum is 0. How many numbers do we need to get the 0? We only need one number. We get 8. If we use two numbers, we get 6, 8 plus 8, 16, etc. To get zeros, we need at least 5. Correct? After we get the 0, we keep 4 in the mind, because to get the next 0 in the 10th place from 4th, we can get base 2, since that's also correct. Okay, okay. Uh, Several digits are written, signs are inserted. How it is done, for example? Okay, so they wanted to find the solution which uses minimum number of eights. Okay, to get the next zero in the tens place from 10, we need to add at least two eights, since 8 plus 8 16 plus 4 is going to be 20. Hmm. We need two in mind, as we need only one more 8 to get 10. Actually, they want to convey a very important information. We got 4 here. So to get 0 here, we need at least 6. So So we need two eights because two eights, one six. The last six and the remaining four will add to give us zero, and we will get two again, which will be kept in mind. Right, here it is told two again, which will be kept in mind, and to get zero here, we need another eight. So we need one eight, one more eight. So 888, 88, and three eights will give us 1000. The problem is solved. 8 plus 8 plus 8 plus 88 plus 888 is equal to 1000. All A denotes some digits, all B denotes another digit, and C denotes the third digit. What are these digits? Okay, so us to say, they want to say that A plus B gives us C, adding two numbers and getting different results is obviously not possible. So actually A plus B is B minus. Okay, I have not I have not taken a look on the solution of this problem. So A C, right? So A plus B is C. C is the last digit, and keep in mind that one of the digit and A minus C. Okay, so A plus B, if is of two digits, then the first digit is A minus C, and the second digit is C, right? Also, we need sum of A plus B to be greater than 10. Sum of A plus B greater than 10. Greater or equal to 10. So obviously A plus B is going to be greater than or equal to 10. Okay. If I put A is equals to 10, B is equals to 10, B is equals to 11, let us say, and try to add these. Oh, okay. I need two numbers which are less than 10, but sum of them is going to be greater than 10. So I can't assume A equal to 10, B equal to 11, obviously. So let us assume 6 and 7. 6 and 7. Okay. So 6, 6, 6, 7, 7, 7. 6 plus 7 is going to give us 13. 6 plus 7, 13, 14. Okay. So So like this, we are going to get a bunch of numbers. We are going to get a group of numbers which will be valid if put in the places of AA, if put in the places of ABC. No, 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 no. 5. I can't find it. It's 5 and 9. If we put 5, A equals to 5 and B is equals to 9, 5, 5, 5, 9, 9, 9, 5 plus 9, 13, 5 plus 9 plus 1, what? Okay. Oh, oh, oh. 5 plus 9, 14. 5 plus 9 plus 1, 15. 1, 5, 5, 4. No, it's still not 5 plus 9. These are some of the problems cause of which I came to this book. Okay, with this problem, they actually want to generalize this concept, which we used in the previous example. There were numbers, so it was pretty easy for us to know what, how can we make it. But first of all, we have to make a plus b equals to c, right? Let us assume a plus. Let us know that a plus b equals to c. Next, we have to make a plus b equals to a. So for making a, how much? Okay, let us treat it like x carry draw. Actually, I did use it. Why is it not really bad at drawing by mousepad? But still, let us try. A, 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 B, 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 C and C. Oh, sorry. A, A and C. This is what I want to say, that if we put A plus B equals to C, then let us assume there has been a carry that is of, let us say n. N is something which was a carry. Right. This is a carry. Let us say n. N is the carry. So basically, A plus B plus B. If you can understand what I have written, is equals to NC, where N being the first digit, C being the second digit. Okay. Okay. And similarly, the N is also going to be here. So I want A plus B, sum of A plus B to be greater than or equal to 10. No, I want sum of A plus B to be exactly. The problem arises. Okay, okay, I did it wrong. Here. So n goes here, and another n goes here. So I also want A plus B should give us A. That also means A plus B gives us NC, and also A is greater than C. The information that I'm going to pull out from here is also greater than C, right? A greater than C, A plus B equals to NC, right? I shouldn't be wasting so much time here. I should not consider it wasted. And also A plus B plus B plus N is equals to AA. So basically, from second and third, NC plus N is equals to AA. Right? These are all of the equations that can be extracted, that can be pulled out from there. Now we have to see how what is the number that satisfies, what are the digits that satisfy this. I want A plus B equals to AA. We got two numbers. The permutation combination of two numbers is going to be if you got 10 options for A, 10 options for B, and first of all, 10 options for A, 10 options for C. So, so 2 to the power 10 divided by 2 to the power 10. That is 1 with 2 for square. Got a lot of options, got a lot of permutation combinations. So obviously this question will be solved by permutation combination, not by trying, not by hit and try method, because that's going to be too long. That is going to be too time consuming. I'm struggling on question number 2. Actually, I'm not struggling. I did miss one thing here. Also, A plus B will be greater or equal to 10, which means NC is greater than equal to 10. A is greater than C. So the minimum value A can have is 1, C can have is 0, and can have is 1. Also A plus B should be greater than equal to 10. So minimum value B can have is 9. So A plus B, 1 plus 9 is equals to NC, that is 10. And also 9 plus 1, 9 plus 1 plus 1 is equals to AA, 1, 2. Wrong. Even for minimum values, this is not true. So if I put C is equals to A equals to 0, C equals to 0, A plus B is equals to 10, A plus B is equals to 10, and C is equals to 0, N is equals to 0. So 10 is going to be AA, which further is not true. So basically, this is not true. Huh. Okay, so why did I miss it? Why was I not able to solve it? What was the flaw in my thinking? Let us see that. I was busy at my phone for some time. First of all, A denotes 1 because no other digit can appear as a carry in the thousand position of the result. Huh? Because no other digit can appear as a carry in the thousands position of result. It's 41, 1241. First of all, A denotes 1. Why this is true? This actually true. This is actually true. Oh yes, it is true. I understand it why it's true. We can't get a non-zero carry. We can't get a carry greater than 2. We can't get a carry. A and B has to be between 1, 0 and 9. So even if we add 9 and 9, we are going to get 18. So there is no possibility, there is no ever any possibility that our carry can go beyond our this digit can go beyond 1. The maximum value that it can attain is 1. The maximum, not the maximum, the only value that it can attain is the 1. Value 1. And this is pretty clear, this is pretty evident. Okay. What is this? What is this? Oh, audio output capture. What about application audio capture, browser, color scale, display capture, game capture, image, media source? What about browser? Okay. Nope. 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 What about this? Okay. I can access it here too. This is time waste. Only let us come to here. The actual thing. Hmm. So we should have already guessed that A denotes 1. Right. And we have already made here that A plus B should be greater than equal to 10. So the minimum value that B can have is 9. Right. So A plus B should be equal to NC. The minimum value that N can have is 1. The minimum value that C can have is 0. N can only have 1. N can only be 1. The minimum value that C can have is 0. And this equation, these are only true for a plus b plus n. So a is 1, b is 9, 9 n is 1, we get a which is 1 1. Perfect. It's 1 1 1 and 9 9 9. A is 1 1 1, b is 9 9 9. The multiplication, uh, okay, I somewhat understood. I got a insight how to proceed these problems. The multiplication table and multiplication algorithm. Okay, input, audio input capture. Okay. To compute the product, say 17 and 38, we draw a picture of 17 rows, each containing 38 points. Okay. But of course, nobody does this. We know an easier method of multiplicating using the positional system. Multiplication algorithm is based on the multiplication table for digits and requires that you memorize the table. There is, sorry, no way around it. And if on being asked what is 7 times 8 in middle of night, you cannot answer 56 immediately and instead try to add up 7 8 halves. 7 8 half asleep as are unable to help you. Some good news, however, you don't need to memorize the 17 into 38. Instead, you can compute it in two different ways. That's it. Both results are equal. The immediate results are different as lucky coincidences. On 36, 51, 646. A boy claims that he can multiply any three-digit number by 1001 instantly. His classmate says into 715. He gets the answer immediately. Multiplying with binary, what it is. So this kind of numbers multiplicating with numbers which only contain ones and zeros. Okay, okay. Take care of the information that is given here, which is that any three-digit numbers. Okay, 1001. It's simple. It's pretty simple. Like multiplying 715 with 1000. Put three zeros after it, and it would be 715 715. Obviously, why it took me that much of time? Hmm. 1010101001. It's like adding 57 with 570. Uh, 570 plus 57. It's like this one is adding 57 plus 570 plus 57 plus 570 plus 5700, 57 557, 5700 plus 57. Ah, have I done any mistake? This is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 ones and zeros. 1, 0, 1, 0, 1, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it would be 1, 0, 2, 3, 4, 5, 6, 7, 8. 8 plus 1, 0, 0, 0, 0, 0, 0, 6, 8, 6, then 1, 10 is to the power 9, 10 is to the power 8 plus 10 is to the power 6 plus 10 is to the power 4 plus 10 is to the power 2 plus 10 plus 1 multiplied by 57. So 57 followed by 8 zeros plus 57 followed by 6 zeros plus 57 followed by 4 zeros plus 57 followed by 2 zeros plus 57 is going to give us the answer of it. But why would anybody do it this way? They actually won't explain something. Hmm. I should actually go and sleep at this moment. This is already done 57. So it will be 57, 57, 57, 57, 57. Answer is going to be 57, 57, 57, 57, 57, 57. Multiply 10230450. Okay, so we got things to be reversed. There is a pattern here, there is a pattern here, and also here. We got a lot of problems here. They did say that we are going to give solutions of problem which will be used further also. Actually, it's 1 a.m. I should go and sleep. I have only read around 1, 2, 3, 4, 5 pages. I got hit with some pretty good problems, so it should probably go and sleep at this moment. There's a lot of this book. So okay, bye bye. See you soon. See you somewhere. Sometimes else. Bye.